The assumption that hyperthermia is an old method is wrong. Hyperthermia, as I see it, has been examined in clinical studies sincerely since the middle of the 80s. In my opinion, hyperthermia is a very important field of research, as we urgently need another modality in the struggle against carcinoma. The result already received for a 5-year follow-up visit for a 1991 study shows that about 50% of the patients have been surviving free of metastasis. At the moment, we are definitely using the algorithms, which are the fastest worldwide. We have developed them in the application of hypothermia. The principal effects of hypothermia are based basically on 3 therapeutic mechanisms. The first one is the direct one with the cytotoxic effect of hypothermia on tumor cells using a temperature above 42.5 degrees Celsius, in effect, direct heat damage. The second effect, which is of special interest to oncology, is the enhanced effectiveness of chemotherapy and radiotherapy with heat. The third newly discovered effect, which becomes increasingly obvious, is a stimulation of the immune system.
Vor der eigentlichen Durchführung der regionalen Tiefenhyperthermie in Kombination mit Chemotherapie.
Prior to an actual treatment of the regional deep hypothermia in combination with chemotherapy, as we perform the treatment in Grosshavn, all actual clinical findings and examination results have to be received. This provides us the assurance that all critical organs such as liver, kidneys, and the heart are protected from neurological disturbances before we start with the actual planning of hypothermia. At first, we need information on the anatomy of the patient, and we obtain it in the form of a 3-dimensional image file, which we generate by computer tomography or magnet resonance tomography. This data is put together in a 50-slice stacked setup form from the CT, which is transferred to our computer platform Silicon Graphics via our own network. This displays the tumor and includes the bones, muscle, fat, intestine, bladder, liver, kidneys, and other organs.
A honeycomb grid separates the therapy unit and the control console. Here the radio transmitter of 1,000 watts is controlled and the spatial power distribution in the body is controlled. By transmitting the radio waves in the tissue, the actual heating, hyperthermia, is generated. Klinikum Charité der Humboldt-Universität, Berlin. Here in the Department of Hyperthermia, the regional deep hyperthermia in combination with radiotherapy is performed.
Our patient has a locally advanced carcinoma of the prostate. You can also recognize the enlarged prostate. Even on the CT, there is a spreading into the tissue surrounding the prostate.
Regional hyperthermia is used to treat deep-seated tumors of the pelvis or the abdomen by heating the whole body regions at a temperature higher than 42 Celsius. The aim is the reduction of tumors. Catheters are placed and thermal sensors are inserted to contact the tumor in the rectum, the bladder, or in the uterus. Thin membrane bolus compartments are deionized water to improve the transfer of the electromagnetic field to the patient. The applicator is located in the area of the tumor. The bolus is filled with water. The newly developed BSD 2000 3D hypothermia system with the integrated planning system HyperPlan first enables the oncologist and radiotherapist to obtain an optimized access to many tumor positions. The planning software operates with the anatomy of the patient, which is received as CT or MR image files, and calculates for each tumor position the optimized phase and amplitude adjustment. The Sigma Eye applicator guarantees a 3-dimensional power focus on the tumor area and, as a result, an optimal treatment. A network of temperature probes and electrical field sensors ensures the quality standard, according to the guidelines of the European Society for Hyperthermia. The first systems of this new generation are already in operation at the university clinics of Rotterdam, Berlin, and Munich.
There is a heating phase period during which the tumor reaches therapeutic temperature, and this generally is less than 30 minutes. After 30 minutes, therapeutic time begins and continues for a maximum of 60 minutes.
A relatively new development has been observed. The development of thermal shock proteins is initiated by hyperthermia. After a short while, the thermal shock proteins emerge on the cell surface of tumors. As a consequence, cells of the indigenous immunologic system are activated and can now destroy tumor cells, which carry such thermal shock molecules.
We have
performed about 2,500 treatments at the Klinikum Großhadern, and can naturally look back on a learning phase during the 80s. Today we can conclude that deep hypothermia is a method with very few side effects. We have less than 5% serious side effects, such as bleedings, burns, and changes in the renal and hepatic function. We point out to our patients during consultation before treatment the fact that the percentage is lower than 5%, and we have observed that the side effects are also lower than 2% during the last 200 to 300 treatments. The patient is also informed that the side effects of chemotherapy are not increased by heating.
Intensive power localization of the energy field, or hotspots, can be generated at the tissue interface. In order to avoid such hot areas, an adaptive simulation procedure is utilized. The second step is to calculate the temperature distribution. At this point, the effect of heat transport through the blood is included, and optimal antenna energy parameters are calculated, which minimizes the heating of the tumor and minimizes the hotspots in the healthy tissue.
An optimal planning with better ability to control the radiating power will certainly lead to a condition where we are delivering hardly any hotspots and thus reducing the already low side effects to zero.
Contact Konrad Susse Syndrome in Berlin for information regarding this technology. The Department of Visual Parallel Arithmetic Technique.
Hyperplan is an integrated software system to plan regional hypothermia treatments. It allows us to read patient data and perform segmenting, in effect to separate and identify the muscle tissue, fat, and bone, and locate the tumor volume. Then a tetrahedron grid is drawn up, and electromagnetic fields are calculated by use of improved finite element methods. Finally, an optimization is performed to allow the physician to operate and direct the hypothermia equipment to treat optimally. The tumors and their different positions determine which applicator is to be used to transmit energy to the body. The Sigma 30 is used to treat the extremities. The Sigma 40 is now being used to treat children in Munich for the first time worldwide. The number on Sigma 30 and Sigma 40 indicates the diameter of the equipment and the opening of the applicator. For adults, we have used the larger Sigma 60 for deep-seated tumors in the pelvis and abdomen. A new development of BSD is the Sigma I applicator. This is a kind of eye-shaped applicator which has already been used for clinical treatments. It is a very innovative development which also allows a very different field distribution. It is an improvement which allows the physician to treat abdominal tumors and also those in the pelvic region.